Alright, so number 1. A certain calculus student hit his calculus teacher in the head with a snowball. If the snowball is melting at a rate of 10 cubic feet per minute, at what rate is the radius changing when the snowball's radius is 2 feet? So I already drew my snowball over here, and so what is given is that our radius is 2 feet. The snowball is melting at a rate of 10 cubic feet per minute, so that would mean that our dV dt is 10 cubic feet per minute, but since it's melting, it's going to be negative. Okay, so given over here is our radius is 2 feet. I'm just rewriting it over here. Our dV dt is going to be negative 10 feet cubed per minute. And what do we want to know? We want to know at what rate is the radius changing when the snowball's radius is 2 feet. So we basically want to know the rate of the radius changing. So we want to know our dr dt. The equation we're going to be using is the volume of a sphere because the snowball is a sphere. And so the equation is b equals 4/3 pi r cubed. So that's what we have so far. And to solve it, we're just going to take the derivative of this equation. So our dv dt equals just the derivative of 4/3 pi r cubed, and we're going to times that by our rate. We're doing this according to our chain rule. So dv dt, the derivative of this entire equation would be 4 pi r squared times our dr dt. And if we plug in our numbers over here, our dv dt, that was our negative 10, equals 4 pi, our radius is 2, squared times dr dt. So we move up over here. Negative 10 equals our 4, and then 2 squared is just 4, and then 4 times 4 is just 16. So it'll be 16 pi dr dt. Get dr dt by itself, so we're going to divide both sides by 16 pi. That cancels out, so our dr dt would be negative 10 over 16 pi, which then just simplifies to 5 and 8. So our dr dt would be negative 5 over 8 pi feet per minute. So the rate in which the radius is changing is negative 5 over 8 pi feet per minute when the radius is 2. Alright, number 2. A baseball diamond is 90 square feet. Coach runs from first base to second base at 25 feet per second. How fast is he moving away from home plate when he is 30 feet from first base? So I already drew my little baseball diamond here. And so what is given is our x and y values. And I kind of drew it like on a grid so I don't get confused, you know, my x and my y's. And so x, which is 90 feet, x equals 90 feet. And then our y would be 30 feet from first base. So 30 feet. And he's running at a rate of 25 feet per second, which is just our dy over dt, which is 25 feet per second. Writing it really small. Okay, so I'm just gonna rewrite our given over here. So x equals 90, y equals 30, and our dy dt is 25 feet per second. And what do we want to know? We want to know how fast he is moving away from home plate when he's already 30 feet from first base. And so we want to know our dz dt, or the rate of, you know, how fast he's moving away from home plate. And the equation we're going to be using, since we have our x, y, and we're trying to find our z value, would be x squared plus y squared equals z squared. And so now we're going to work this out. We're going to plug in our 90 and our 30 to find the z value. And so we go x squared plus y squared equals z squared. X is 90 plus y is 30 equals z squared. 90 squared is 8100, 30 squared is 900 equals z squared. That right here is 9,000 equals z squared square root, and z, we simplify that down, would be 30 root 10. And that would be our z. And now we just find the derivative of this equation. And once you find the derivative of this equation, just plug in the values and you will find your dz. So we're going to come over here. X squared plus y squared equals z squared. Instead, take the derivative. 2x plus 2y dy dt equals 2z dz dt. This would, well, actually, we're going to plug in all our numbers. 2 times 90 plus 2 times 30 times dy dt, which is just 25, equals 2 times z, which we found was 30 root 10, dz dt. And then this value is actually just going to be 0. So then it would be 2 times 30 times 25, which is just 1500, equals 2 times 30 root 10, which is just going to be 60 root 10 times dz dt. Going to divide all that, 60 root 10, 60 root 10, because you're trying to isolate our dz dt to get our value. This simplifies to, that simplifies to 1, this simplifies to 25, and it'll be 25 over root 10 equals our dz dt. So the rate of which the coach is moving away from home plate is 25 over root 10 feet per second when he is 30 feet from first base. And there we go, all our work. All right, number 3. Water flows at a rate of 8 cubic feet per minute into a cylinder with a radius of 4. How fast is the water level rising? So I already drew my cylinder over here. And what is given is that our radius of the cylinder is going to be 4 feet. And that the water is flowing at a rate of 8 cubic feet per minute. So our dV dt is going to be 8 cubic feet per minute. I'm just going to rewrite the radius over here. 4 feet. And what do we want to know? We want to know how fast the water level is rising. So we want to find our dH dt because we want to find the height of how fast it's rising. The equation we're going to use is the volume of the cylinder equation. So V equals pi r squared h. And here the radius is not going to change because the height, we're trying to find how the water level is rising. The radius won't change, so we can actually plug in this 4 into the radius equation over here. So V equals pi r squared h. So V equals pi 4 squared h. V equals 16 pi h. Then all you gotta do is find the derivative of this entire equation now. dV dt equals 16 pi dH dt. We saw that our dV dt is 8 cubic feet per minute because that's what was given. 8 equals 16 pi dH dt. Divide by 16 pi to isolate dH dt. This was going to simplify over 1, not 2. I wrote 2. Don't know why I wrote 2. 1 over 2. It'll be 1 over 2 pi equals dH dt. And it's rising at a rate of feet per minute, I believe. Yes. So the water level is rising at a rate of 1 over 2 pi feet per minute when the radius is 4. And there it is, all our work.